So anyhow, it's time to introduce today's first speaker. Roman Bezrukavnikov is going to tell us about representation, theoretic geometry of algebraic symplectic varieties.
Thank you very much. And I would like to thank the organizers. That's a great opportunity to share these ideas. And the goal of my talk is to present some algebro-geometric structure arising in geometric representation theory. And maybe my title is broader than my content, meaning that we're focusing on a specific area within geometric representation theory, Каждоновистик theory, and my experience writing on it. So what do I mean by Каждоновистик theory? So let me spend a few minutes explaining that. So this is an area of research which started from the proof of Каждоновистик conjectures, which already goes way back, 1980. And I will give a very brief impressionistic view on that story. So the conjectures themselves, they describe the basis of irreducible objects in the Grothendieck group of a certain category of representations. And I will not even go into details of what is this category. So there are some representations we want to understand. They form a abelian category. There are finitely many reducible objects. And there you go. And so it's called category O, but that's not important. But I want to emphasize the key features that appear in this story. And one feature that is the big group of symmetries of the derived category of our representation category. And the specific group that is acting there, and I will say a bit more precise what it is in a few minutes, but the specific group is, it has different, there are different ways to think about it, and different descriptions, including presentation by generates and relations, but there is also a geometric way. It's a fundamental, a very natural description is as a fundamental group of some variety, a manifold. But the definition of the action does not work with that. Incarnation is purely combinatorial. And part of what I'm going to address is how to generalize and geometrize that. Then the other feature of that story is, so it's important how this group action interacts with the abelian category sitting inside the derived category. And the technical kind of a concept encompassing this data of abelian category, of an abelian category inside a derived category, just basically the recording kind of nice way to record the data of abelian category inside a derived category is called T-structure. And so the symmetries do not preserve the structure. They are not T-exact, in other words. They don't send modules to modules. They send modules to complexes.
The microphone, sure, you can talk into that one.
Should not, or should?
You should talk into that microphone.
Oh, okay, sorry. So yes, I was saying it's not T-exact, but somehow the T-structure interacts with the symmetries in a control way. So I'm the sentence that you see on the screen, that it's numerically controlled, is deliberately vague. But for those who work in on derived categories and of coherent sheaves and probably have seen regional stability conditions, that's what that should bring to mind, but I will be more precise later. And then the final point I want to mention is that, maybe if you have heard one sentence about Каждоновистик theory, maybe that sentence is likely said that it has to do with Q deformations. So there is this Grothendieck group that of the category that is easy to describe. And when linguistic formulated conjectures, the kind of, it's all hinges on Q deformation of that group. But the formulation hinges on the Q deformation, and the proof hinges on the interpretation of that Q deformation in terms of Hodge of Frobenius weights, and then the general theorems in algebraic geometry, which expressing some deep properties of those structures of the homology. Okay, this was a very kind of bird's eye view, and I will give slightly more detailed, slightly more concrete overview in a second. But again, I mean, my hope in presenting this to you is that already at this level, it can resemble some of the structures in algebraic geometry that people are working with these days. And my plan is describe a generalization and extension of the story, where instead of this category of representations that maybe not many of you care about, we work with derived category of coherent sheaves on an algebraic variety, and maybe more of you care about. And then the features that pop up there, structures that pop up there are stability conditions in the sense of Bridgeland or some closely related sense, and then Hodge structures, and then equivariant quantum cohomology and stable envelopes. And so this is something that was not there in the 80s, but this is a new kind of chapter of enumerative algebraic geometry that connects to these structures. So this is my plan. Okay, so now I'm start to say something slightly more concrete. So I still want to spend a few minutes recalling this old story, which a prototype for some of the things I will talk about. So, okay, there is this reproductive group or a subgroup. We can we'll lose nothing today if we think just about invertible matrices and upper triangular matrices. And then there is a category of B equivariant D modules on G mod B, and it's by Bernstein theorem is identified with category OR. Now, I put this word here, but this is the only time that D modules will be mentioned today. So if that's not your thing, you're just fine. But maybe one one point to know about them is that these are obtained, so this is quantized version of sheaves on the cotangent bundle. So you have the structure sheaf of the cotangent bundle. Suppose some sheaf of algebras, you deform it, you get a ring of differential operators, and the modules of this ring are the D modules. So that's helpful to know, but otherwise you won't use them. But then there is an easy fact, just the count of orbits. For example, I didn't write it, but for the group GLN, there is this one of this, decompositions we teach in linear algebra. So every matrix is a product of upper triangular permutation and another upper triangular. And in general, G mod B mod B is the Weil group, Sn for GLN. And from this easy fact, follows another easy fact that this Grothendieck group, again, I brought the top, I write K for the Grothendieck group. So the Grothendieck group of my representation is just the group algebra of that finite group. So for SLN is this very concrete basis of n factorial elements. And then, as I mentioned before, the problem that Grothendieck posed is to describe the basis of irreducibles. And again, I'm not recording this to in detail, but I want to mention that the key ingredients in the proof. And so now I'm going into this, just saying the same kind of point about Q deformation and weights in a slightly more precise way. So what this paragraph says here is that our category, well, it's some category which from basic algebra can be expressed as category of modules over a finite dimensional associative algebra. And the defect that turns out to be equivalent to those conjectures is that this algebra has a positive grading, which just means that it has a grading where negative components are zero and the neutral zeroth component is semi-simple. And the way, and so this grading produces the Q deformation of the K group. So the K group of graded modules is Q deformation of the K group of non-graded modules, where Q just is the operator of shift of grading. And somehow what will be relevant later is a similar fact at the geometric level, where we'll have an algebraic variety with a GM action, and then the equivariant K group will be a Q deformation of the non-equivariant K group. And the another key feature, which I also mentioned, but now let's say what it is. And so there's an action of the break group. So what is the break group? It's a break group corresponding to this G, so it can be described, as I said, by generates and relations, which I don't recall, but it can also be described, more relevant for this talk, as fundamental group of the regular part of the carton of the diagonal of the algebra, quotient by W. So I take this vector space, I remove a bunch of hyperplanes, you know, as walls, and I quotient by the symmetries, and I get the break group. So for type A, for GLN, this is the usual break group that appear in many undergraduate curricula. Just you can draw using threads in the space, and it is fundamental group of configuration space, just because configuration space is exactly this n coordinates of the and diagonal matrix of your and entries of your diagonal matrix can be thought of as giving you a configuration of points in C, and the matrix is regular, meaning exactly when it's actually configuration, the points are distinct. And so, yeah, so here is a picture for us three. So these are the three, well, in this case, it's two-dimensional, so instead of hyperplane, I can say a line, so I remove these lines, or other complexifications. And then I can think of an element in the break group as a path connecting one of those cones, real cones, to the other. Because the thing is that it's easier to draw a vector space than a vector space modular finite group. So you should kind of, in your mind, you should identify all these different cones, so they are the same in the quotient. So any path in the complex domain which bypasses such a hyperplane, and it starts in one and one cone, and ends in the other, determines an element of fundamental group. So here is a little blue path like that. So it's passes in the complex domain around this line. Okay. And so without going into details, the action is, again, it's generated by so-called derived sheaf functors. So basically, the definition doesn't work with, again, as I said, with the fundamental group picture. It works with this combinatorial algebraic data, and namely every integral point in any of these cones determines well, a quantization of my cotangent bundle determines, and then they connected by derived sheaf functors, and when we sort of cross the wall in this sense from integral weight in one cone to integral weight in another cone, we get the generator, action of the generator. All right, so I'm done with recording the classical story. And now I'm on to my kind of program. So I want to describe the similar structures in derived category of coherent sheaves. And X will be algebraic symplectic variety. But I will spend much time, maybe most of my time, remaining time on the specific example, and then I'll talk about generalizing it. So this part one is talking about this particular case. And it's still tied to presentation theory very closely. So you would start with this cotangent bundle of the flat variety, and it has a g-action and the moment map, whose target is a set of nilpotent elements in the in my Lie algebra. So this is a resolution of singularities, so-called Springer resolution. It's a prepend, and in fact, Y is a symplectic singularity and X is a symplectic resolution. And so this example contains kind of other, a small example is inside, so you can just take, so Gx and N with finitely many orbits, you can take a slice to an important orbit and just take its pre-image. So these are my examples for the next 15 minutes or so. And to something concrete that probably every geometer have seen, is there is, if a group is simple, there is a unique codimension 2 orbit. And when, in that case, what you get is a minimal resolution of a rational surface singularity. People say Kleinian, Duval, or etc. So here's a picture. So it's a resolution of surface singularity with just isolated singularity, and it's isomorphism everywhere. But over this single point, you get a chain. I mean, in general, it's kind of a collection, union of projective lines with this nodal singularity, so connected in this way. So every circle symbolizes a copy of P1, and yeah, this is for SLN, there will be n-1 lines. So this is a picture for SL4. Okay. So now I'm starting to state a long theorem, which basically lists various structures that we observe here that were led to consider the problems in representation theory. And yeah, I'm sorry, many of these results are not at all recent, but so this is a survey talk. But yeah, there will be some more recent or forthcoming results. On the average, maybe the date is okay. Yeah, so one thing, yeah, I'll list it in my collaborators, so maybe I don't need to read it out loud. The names. So this X has the following structure. So first of all, we have an action of the affine Weil group. So this is some sort of souped up version of the break group. So now it's the pictures on the next slide, but so for for GLN, this is now configuration space of points, pi1 of configuration space of points on C star. So people sometimes draw it as braids were drawn on a cylinder. So kind of a thread can go around. So this is the picture. So now we have the affine configuration where there are also shifts of this hyperplanes, lines in this case. And just as in the previous story, point apart from one Elkov to another in the defines a path on the quotient, so an element in the group. Yeah, and then there is it's not on the slide, but there is a very similar way to define it using D modules and positive characteristic. But I promised you not to mention it again in the slides. I'm just saying it verbally. And so if in this two-dimensional case that I just flashed at you, it's been considered well before us, and it's just generated by spherical reflections at the structure shapes of this lines. So basically to each of these lines that correspond to spherical objects in your category, and there is a sort of spherical reflection that you can draw, that you can define, and it is this is the auto equivalence, and then there are twists by line bundles, and together they generate this group. Okay, so then, yeah, I'm just a kind of quick remark that will come up later, that we can just rewrite. So everything is kind of periodic. This picture is periodic. So why don't I quotient by this lattice? And then if I quotient vector space by lattice, then by exponential map, I get the torus. And so I get some sort of thing on now an algebraic variety, right? So the complement to infinite collection of hyperplanes was not algebraic. Now this thing is algebraic. So this is just an algebraic torus without a few codimension one subtorus removed. And so I get double equivariant. I get representation of a fundamental group of that thing. Well, W, but I can think of this as double equivariant local system of categories on that algebraic variety. And okay, so this was the first piece of structure. Now, the second piece has to do with these non-commutative resolutions. And this is like a tilting vector bundle, tilting generator for the derived category, which gives a derived equivalence with a non-commutative resolution, which I dubbed at some point non-commutative Springer resolution. And then so we have this derived category, we have outer equivalences, and then we have some T structure, right? So we have this equivalence, and we can transport the T structure from the right-hand side to the left-hand side. And it turns out that you can fit it in a stability, a Bridgeland stability story. So to connect to that story, I need to pass to some finite type category where homes are finite dimensional. Well, I can just do it by focusing on sheaves with support, set theoretic support on the central fiber. And then the claim is that there is a connected, so this T structure that I get there, it's actually this finite type. So there's there's a T structure where every object in the heart has finite length. So it's generated by this irreducible. So it's very easy to produce a Bridgeland stability for such a thing. You just assign a point in the upper half plane. But the point is that, in fact, if you do it that way, then you get a point in some connected sub space in stability manifold invariant under the big group action. So this, what's written here, I mean, tau heart is just a part of the T structure. It's not, and then what the sentence is saying is that it sits in a connected part in the stabilities. Invariant under a fine one group, a fine great group. So I hope this makes sense to people who have worked with Bridgeland stabilities and derived categories and coherent sheaves. For others, there will be an alternative description of related structure, which will be kind of self-contained. So bear with me. And so, I just want to say that the central charge for this stability manifold is they all kind of come from second cohomology. So I guess that's in the literature what people called stringy modular space. But sort of a closely related or maybe equivalent structure is basically a collection of T structures indexed by alkovs permuted by BFI. But then the kind of heart of this is that the key point is how they're related for different alkovs. So again, so there are for every alkov we have a T structure, and they're send one to another by appropriate element of the break group. And now I want to describe some precise a relation between them, kind of relation as you pass from an alkov to the next one, which it closely relates to this Bridgeland stability story, and also makes this vague sentence on the first slide about being able to numerically control the change of T structure makes it more precise. So what I'm trying to say is that kind of, again, I'm still in the middle of this theorem, expanding part C, maybe also D and E. Yeah, that the T structures in the neighboring alkovs are related by perverse equivalences. And what I'm trying to say on the slide, so on the next slide, I will recall what this means. And, but what I'm trying to say here is that in the paper where we relate this to just Bridgeland stability, just if you only want to prove the statement on the previous slide about connected piece in Bridgeland stability, invariant and a BFI, you only need to know what happens when you cross codimension 1 wall. However, it can be refined, so there is this kind of less refined blue information having to do with this blue symbol S and blue part here, but there is a refined green information which has to do with the green part crossing a high codimensional wall. Well, I will hopefully it will make some sense after the next slide, but again, the concept that I'm not explaining in full, but which encompasses this, is this real variation of stability defined in my paper with Anna Merkovich. And at least the way I see it is that it kind of implements intuition, kind of similar to the Bridgeland's definition, but technically it's somewhat different. And okay, so yeah, what the previous slide said, that there's some perverse equivalence is governed by central charge, but I'm making it precise on this slide. So when I say that something is, so first of all, the central charges is just polynomial map from this vector space to the dual space of the K group. And there are two kind of key axioms. One is that if I take a point in the alkov and I evaluate the central charge and I pair to an object in the heart, I get a positive number. If a non-zero object in the heart, I get a positive number. And then the next more interesting axiom has to do with a filtration that this data defines on this abelian category. Namely, I kind of, given that first property, I just get a subcategory, full subcategory in a abelian category consisting of objects for which this central charge polynomial vanishes at order D on as you approach this face. And I'm using this nice elementary fact. If a sum of two positive polynomials vanishes at order D, then each one of them vanishes at order D, at least D. And this shows that this is a third subcategory, abelian category. And so I get a well-defined filtration. And now having this filtration, I can run this definition of Jean-Rouquier of a perverse equivalence. So this is, the name comes from the fact that a special case of this is the relation between constructible sheaves and perverse sheaves, or also, you can also work with coherent perverse sheaves and coherent sheaves. And there are many other examples, but so here this is sort of example of a different nature. So yeah, basically what it says is that we have this filtration on the categories and have two T structures, but they compatible, they're both compatible with the corresponding filtrations on the derived category, but on GER-I they differ by the shift of by I. So of course, if you've seen definition of perverse sheaves there, it would be exactly this, where the filtration is by dimension of support. But here it's of a different nature. Here it's not kind of. Here it has to do with this vanishing central charge point. And yeah, last line, I leave it as an exercise to relate this to Bridgeland stability condition. If you want a hint, you can ask for one after the talk. Okay, so here I just repeat this. At the top of the page, I just repeat this information. But the C double prime is that so this is repackaging. I mean, yeah. So this is not so much to do with the perverse equivalence. This is just with this collection of T structures, non-commutative resolution indexed by Alkovs, but along the lines of kind of passing from periodic data on the vector space to the data on the torus, I pass to a local system of categories on the dual algebraic torus, and then I get a local system of categories there, so that the stalk at a point on the compact torus is identified with a derived category of non-commutative resolution. And then the relation to actual commutative resolution is best expressed in using a compactification theoretic variety. So basically this collection of configuration of hyperplanes that was on one of the previous slides, it gives a toric compactification. And somehow for every cone, there is a zero-dimensional orbit in this toric compactification. And the nearby stalk at such a point is identified with the derived category of coherent sheaves. So this reformulation will come up later. And then, okay, I promised D and E. So D is, in a way, this is the hardest and deepest part of the story. And this was, I didn't say this, but this kind of was motivated and led to a proof of Lustig's conjectural generalization of Kazdan-Lustig conjectures to representations of the algebras and positive characteristic. But what is more relevant for this talk is that, that it is still proved using Hodge-Frobenius weights, but since we're dealing with coherent sheaves, there are no Hodge-Frobenius weights. So to connect them to some place where they exist, there are additional ideas that were needed, and namely relation to geometry of loop group and local geometric Langlands ideas. So this is the executive summary of my paper with Ivan Merkovich. And okay, so there is this theoretical comment that I'm hoping for I mean, there are indications for relation of these two theoretic, or at least not P-Hodge theory, and I hope that one day there will be a more direct approach using this theory, but that's very, very up in the air, very much up in the air. Okay, and then finally we come to part E. This is the relation to enumerative geometry to quantum cohomology. But to formulate this relation, you need to make one move, which is kind of cheap on the category side. It's quite easy to, there's some additional equivariance, so there's some group acting. I mean, it's better maybe to focus on the action of maximal torus in the group. But actually, the most important thing that's acting is this thing so-called in green, the GM that acts by dilating the fibers of the cotangent bundle. And once you constructed all the things that I listed, you can lift it to the equivariant category. But then you can just decategorify, you can pass to the Grothendieck group. And that turns out to coincide with the monodromy of equivariant quantum connection. And just like in this algebraic picture, it's very important to work with equivariant connection. And again, there is this sort of Hamiltonian torus that you may or may not include. I mean, it gets richer if you do, but that's not as crucial. But the crucial thing is that you include the thing dilating the symplectic form, because otherwise quantum corrections die and the connection becomes rather boring. And again, so this equivariant parameter plays a role of this Q in the Q deformation on the first slide. So this follows from paper of Braverman and Mogilevich. Again, this is all going some years back. All right, so now I'm done with my favorite example, and maybe my old favorite example, and now I can pass to my more recent favorite example. So there's this program, which is already also not very recent, that this should generalize to arbitrary symplectic resolution. And I want to discuss that. So maybe one remark about the statement is, yeah, I hope like the account of the T-Stagimat B gives some information what I mean. But part of what I mean is that there is a local system of categories on the on an algebraic torus, which is H2 of X star. And so so this local system of categories should have this property that if we consider appropriate toric compactification of this torus, then the nearby stock at a zero-dimensional point in this toric variety will be identified with the derived category of a resolution. But the point is that if I have a symplectic singularity Y, then there are different resolutions. And so by Nemikava theory, I mean, which is a special case of minimal model program, they correspond to different cones in H2. And the point is that so there are general conjectures which were proved for symplectic resolutions by Kaledin, which say that given two crepant resolutions of the same variety, you have a derived equivalence. But this kind of encompasses this statement, and also makes it more precise, meaning that it explains to what extent this equivalence should be canonical. That it says that we should get such an equivalence once we fix a homotopy class of a path from neighborhood of one point on the toric variety to the other in the complement to the device. Okay, so yeah, just a few words about the status. So it's partly known for hypertoric variety and Gamage, Green, and Webster, and essentially known for quiver varieties, at least with isolated fixed points. So this is some things are to be written, but the math is there. But I should say that when I say known, it's kind of with a big exception. So this deepest part is still not there. So maybe in the hypertoric case, I managed to do it, but I mean, this positivity of grading is still missing in general. Okay, so maybe I just want to say a few words about the proof of this result. So what are the key ingredients? So first of all, how do we build this local system of categories that I alluded to on this picture? This is this method that also was there in T-Stagimat B case. So there's a quantization in positive characteristic. So basically, so we have this L cups, we delay them by P, and then an integral point in such an ALCOF, it determines a quantization parameter, and then I kind of quantize this variety with with this pick a quantization with this parameter, and then using this p-center phenomena, we get a non-commutative resolution. Non-commutative resolution, a derived equivalent to my commutative resolution. And by the way, the central charge also kind of pops out this construction. And the other, so this allows to produce a local system of categories. But it's from this construction, it's very hard to see why it should be compared, have anything to do with quantum cohomology. And the so this is done using the theory of stable envelopes by various people. So the point is that the stable envelopes are related to Verma modules of the quantization, and on the other hand, by results of Andrei Vedmina and Ganagic, control the quantum connection. So just to make some context, to provide some context to this, I not so much explain as illustrate what the stable envelopes are. So it's a concept developed by several people like Devesh, Andrei Smirnov, and Dan Alperlesner here. And so in different levels of generality precision, there are first homological, okay, theoretic. And there's this, in this work, we use categorical stable envelopes. So this is the picture in the same example of two-dimensional Kleinian singularity. So we have some action of a torus with finitely many fixed points, and then to each fixed point, we're going to assign a Lagrangian, which is drawn here in red. So it's a union of attractors of all of this point and everything below. Well, below means, yeah, it's in the closure of the attractor. And then there is some clever way to, I mean, this is a cycle. I mean, this may be a subvariety, but then there is a clever way to make it into first a cycle, then a K-theory class, and then eventually a coherent sheaf. And these axioms are given by these window conditions. It's characterized by the window conditions which prescribe, say that the torus weights, as you look, if you look at the fiber on any of those fixed points, you have a torus action, and it should be constrained. I mean, the weights should lie in a certain polytope. And in fact, there's a family of these window conditions, and they will correspond, I mean, to an ALCOF in my previous picture will give a specific window condition here. Okay, so this is the summary of those ideas. And maybe I'll spend a few minutes talking about my favorite example. I mean, more recent favorite example. So let's just, something very concrete. Let's just take the Hilbert scheme of points on the plane. And just for simplicity of notation, so we have an action of translation group. Let's just factor it out. So you can say, think it's Hilbert scheme of points centered, so center of mass is 0. So this is a nice example of a symplectic resolution. I'll actually have queer variety, which is covered by the generality I mentioned. So what are these ALCOFs here? So in this case, the space H2 is just the one-dimensional. So instead of those hyperplanes, you just get points. And the points that come up here are these fractions with denominator at most n, except for integers. So they break the line into intervals, which I call stability intervals. And I'm saying that to every, so this is all no. So that to every every interval that corresponds to T structure on the derived category of coherent sheaves on the Hilbert scheme. In particular, the initial interval from -1 over n to 1 over n, this is the T structure that came up in the literature before. So in the work of Mark Heyman, sorry, I should have put his name on the slide too. He proved, constructed a derived equivalence with the coherent, with the orbifold, equivalent coherent sheaves on the flat space. So symmetric power of the plane, well, here it's with a mass centered. So I have this T structure like BKR, actually Heyman's T structure, which is you transport the tautological T structure from the coherent sheaves on the orbifold to the Hilbert scheme. Okay, so this is one thing, but so what about the next interval? The next interval is going to be 1 over n to 1 over n minus 1. So let me tell you about that. And so this one is obtained from the previous one by what I call a Pn, well, Pn minus 1 in this case, semi-reflection. So the point is that this is referring to something in the literature. So Hoibergs and Thomas at some point defined Pn reflection. And now I'm taking a square root of that construction, which I'll explain on the next slide. But first, so where do I get this Pn object? Well, this is actually pretty easy. So, okay, let's look at this Sn equivalent coherent sheaves, the flat space. Let's just take the trivial, just skyscraper with the trivial action. Or if there's also another variant, you could take sine action. Okay, so this is clearly an irreducible object. Now, a little exercise is that this is actually a Pn object in this category, Pn minus 1 object in this category. So to do this exercise, you need to know that if you take symmetric group and take its reflection representation and take its exterior power, then you get an irreducible Sn module. With that in hand, you should be able to do it. So, and now you can do the, you can apply Hoibergs-Thomas construction. So, okay, so this is the picture for n equal to 4. So I have this initial interval I0 from minus 1/4 to 1/4, and then this next one from 1/4 to 1/3. But so, okay, so Hoibergs-Thomas, they define an auto equivalence, and what you need to know about this is that there's nothing more modular the category generated by this Pn object, and the object itself gets shifted by 2. If it's Pn minus 1 reflection, then it's 2n minus 2. But now I'm saying that, and by the way, this automorphism is a part of kind of my structure, meaning that in this case, we get an action of a fundamental group of the complement to all these fractions, which you can, well, modular translation, which you can also think of action of fundamental group of C star without roots of unity of order up to n. But so yeah, you have the action of this fundamental group on the category, and as Pn reflection will be one of the generators, it will actually correspond to the full monodromy. It's not drawn here, but you know, I've drawn this arc going from the first interval to the second, but you can also go back around this 1 over n, and that will be the Pn reflection. But now, to get this new T structure, I actually have to extract square root. No, I cannot extract the square root of the automorphism. But what I can do is, I'm saying that there is a T structure, new T structure, which is halfway in between the original one, the BKR, the Heyman's one, and the image of this BKR under this equivalence. In other words, this is the T structure, which is incised with the old one on the quotient by this object, and the object itself. So what lies in the heart of this new T structure, it's not this, but it's K not shifted by n minus 1. So I don't know if that's written here, maybe not. And well, yeah, I can, will not explain the formal meaning of this word, but maybe it should make some sense to many people here is that I'm thinking of this as a non-commutative Mukaev law, and at other fractions with denominators exactly n, there will be exactly this kind of situation. There will be monodromy is the Pn reflection, Pn minus 1 reflection, and passing from one T structure to the next T structure is Pn minus 1 semi-reflection. And at other fractions, something more complicated is happening in some sort of iterated Mukaev law. Actually, I just want to mention that the key property that you encounter if you try to establish the good properties of this filtration is the strong Lefschetz. Strong Lefschetz for the action of x from k to k, acting on x from no, sorry, x from this, my preferred, sorry, I call it k0 is my Pn object from this object to itself, acting on x from to any other reducer. Okay, let's see. So yeah, my time is almost is over, but I just wanna briefly mention one other aspect of this mirror symmetry. So in many cases we have candidate for mirror symmetry, certainly for T star G mod B and for the equivarieties. But here is an aspect I wanna mention. Okay, so I will skip the details, and I'm advertising the paper. Result in the direction of mirror symmetry for T star G mod B, which is forthcoming. But what I wanna emphasize is that the difficulty in passing to numerics. The thing is that the kind of back like ideas from the 90s, they say that, okay, I have this family of varieties, which is mirror dual to my thing, and then I get an action of the fundamental group on the Foucault category, and then I take Gauss-Manin connection, I get the action of homology. So here I also get an action of Foucault category, but unfortunately Gauss-Manin, kind of the naive Gauss-Manin, it misses this Q deformation. Basically, I still don't know a good way bring in this Q deformation in the Gauss-Manin connection. But what I'm trying to say is that as a partial compensation for that, in this picture, even if I take the naive Gauss-Manin, when I recover the boring specialization of the quantum connection, where I kill this interesting parameter which kills quantum corrections. However, I get a new structure with variation of Hodge structures. And some, okay, so I think I should be wrapping up, so I will not walk you through this long statement of a proposition, but the point here is that it gives some indication that this data captured by this variation of stability is also captured by this variation of Hodge structures on the Gauss-Manin connection of the mirror dual. And skipping the next slide, I'll get here. Thank you.
Any questions for Roman?